Okay, let's get started. I think it's now time. Um, as you know, today you will be presenting your assigned class projects. Uh, Today there will be four presentation. At first, I would like to invite the Nolan, Tyler, and Moses project, gravitational energy storage methods. Like Nolan has some sort of emergency; he needs to leave the class soon. That's why at first I'm inviting his group. So Nolan, Tyler, and Moses, please present your project.
Okay, yeah, that works.
Yeah, I have already permitted, so you can share your screen.
Okay, sure. Yeah, I'll go ahead and share it.
Yeah.
Alrighty. Is everyone able to see the PowerPoint?
Yeah, we can see.
Wonderful. Okay, so today myself, Nolan Robinson, and Moses York will be presenting on gravitational energy storage. This is just an outline of what we'll be talking about. So in short, we'll be talking about what is gravitational energy storage, how it is done, how we actually store energy as gravitational potential energy, and how we apply it, and how this affects us. So starting off with what is gravitational energy storage. So gravitational energy storage in this sense is storing energy as gravitational potential energy. All the way from elementary school and middle school up to college level physics classes, we've learned many of the principles around different forms of energy. As a refresher, energy can be organized into either kinetic or potential energy. Kinetic energy is the energy an object has due to its motion. The ball at the bottom of the slope on the bottom right of the PowerPoint is like the classic example of kinetic energy. Potential energy is the energy an object has due to its relative position due to another object's center of mass. Not due to another, but relative to another object's center of mass, rather. And this can be in the form of elastic potential energy in either a spring, an archer's bow, or a rubber band. We can also see potential energy in the form of electrical potential energy, or voltage, which we as electrical engineering majors are very familiar with. And in today's topic, gravitational potential energy, the potential energy that an object has due to Earth's gravity. The ball at the top of the slope is an example of gravitational potential energy. And we learned from Newton that an object will keep its kinetic or potential energy if no other forces are acting upon it. And this is the basis for energy storage. So in storing energy as gravitational potential energy, some of you may remember from physics class that gravitational potential energy in an object can be found using the equation mg delta h, where m is the mass of the object, g is acceleration due to gravity, and delta h is the relative height of the object from a specified surface. Since the mass of the object and the acceleration due to gravity are both constant, we'll see that gravitational potential energy of an object will increase as its relative height from a surface increases. This means the higher we lift an object, the more gravitational potential energy it will have. Sort of what the diagram is showing on the right, that the ball on the right would have a higher potential energy than the ball on the left. So this is exactly how we store other forms of energy as gravitational potential energy. We'll either lift a heavy mass mechanically or using water and hold it there until we want to release the energy. I will pass it over to Moses to talk about exactly how we do this in the real world.
Sweet. Yeah, and then now we're on to the operating principles. So the operating principles depend on the method being used for each gravitational energy storage unit. Our first one up is the PHES, or the pumped hydroelectric energy storage. For the pumped hydroelectric energy storage, electricity is used to power a pump that generates and stores potential energy. This system allows for both generation and storage modes to be accessed. In the storage mode, whenever the piston is being lifted, the energy is being stored in the potential energy created by the raising of the heavy piston. On the flip side, whenever we like the power output, the piston will begin to drop as water begins to flow up the return line and flow into the PAT. Another principle to note is the PAT configuration acts as either releasing or storing of potential energy, which is caused by either the raising or the dropping of the system. The PAT is known as the pump ass turbine. It is located within the powerhouse hub. The pump turbine displayed in the schematic to the right is the main foundation of the system, allowing kinetic and pressure energy of the fluid to become mechanical energy. The function of the PAT is to be a hydraulic turbine that extracts energy from the water as it flows, and also to become a pump that pushes water through the impeller all the way to the bottom of the container shaft. The PAT runs at a constant speed but consists of a variable torque that controls the flow of the water. The turbine has to run at a rate of around 1,515 RPM just to be able to run at an acceptable frequency. A fully functioning system will have the water begin to flow as a large piston begins to descend down the storage shaft and water underneath begins to move up the return pipe and into the PAT system. The PAT then acts as a generator, allowing potential energy to be created into electrical energy and be discharged out to the nearby grid. With the surplus of electricity that is output, the reversible pump turbine shifts some electricity to power the motor generator to start the process all over again with the raising of the piston with water flow. The system consists primarily of a large piston that is hydraulically lifted and lowered through the use of water channels and gravitational potential energy. And then the next one, so now we're on to graviticity. Graviticity is another example of gravitational energy storage system. The operating principles are similar to the pumped hydroelectric energy storage system, as it is using gravitational potential energy to be either captured, stored, or released as electrical energy. First off, Graviticity, it's actually the name of an Edinburgh firm that is conceptually developing new ways to store energy. Their model takes after their company name. Instead of wanting to create an electrical source from a chemical process, they chose to use physics instead. Their model includes a system of cable and winches that serve a dual purpose of generation and support. These winches and cables are powered from a nearby grid to be able to lift a heavy weight. The raising of the weight increases the gravitational potential energy as the altitude increases. The winches then can release the weight, turning the winches themselves into generators. The energy can either be stored for a long duration or just about until they decide to use it. Once they're ready to give an output power, the electrically driven winches lower the weight and now run as generators, exporting electricity back to the grid. The saying, anything goes up must come down, is quite a notable phrase for this gravitational energy system. The configurable output now is dependent on the rate of which the large mass is lowered. If it stays at a normal rate, it could power up to 1,300 homes for about 2 hours, which is roughly 9 to 10 megawatts per hour. With an improved sophisticated winch system, it could release the weight at a faster rate, which in turn would deliver short bursts of high power. In Scotland, where Edinburgh is the capital, electrical networks need to usually stabilize at a grid to 50 hertz. And Graviticity is pretty suited for this because they have a fast response time of less than a second just for full power. This cable and winch system allows for discharging and recharging of the gravitational potential energy again and again. And the next one, and we're on to the construction and components. Next on the agenda is the construction and the makeup of some of these gravitational energy storage systems. For the PHES, it needs a large landscape for building and implementing the entire system. Notably, a large reservation of water would be key when locating a prime spot for containing a water source. The last major landscape-related construction piece would be the large underground storage shaft for the piston and water system. The shaft is filled with water that acts as a medium for energy transfer. The huge vertical shaft is fitted with a large steel piston lined with reinforced rock and concrete just to be able to withstand the hydraulic pressure. Those two aspects are essential for the device to operate as it moves vertically up and down. The shaft would also have to include a separate channel returning back to the ground level so water would flow freely up and down this return pipe to be able to connect to the PAT that is above ground. Now for the Graviticity system, the construction is a bit simpler. It needs a large chunk of land to be able to have a powerhouse system of cable and winches. Similar to the PHE system, it needs a large hole in the ground. This large vertical hole needs to consist of concrete and steel walls to line and be able to withstand the system of strong cables and weights. Now the weight configuration can be anywhere from 500 to 5,000 tons. The heavier the weight, the more energy it stores, which would be ideal, but with an even larger weight, you need to have an even larger tunnel. Graviticity has said that they would like to repurpose unmade mine shafts and bring them back into use. The shaft depths can be from 150 meters all the way to 1,500 meters. This gives them a lot of flexibility within their dimensions alone for either volume depending on the weight or the height depending on the storage shaft. And then the last final component pretty much is both of these would have to include a grid connection that both these systems would be connected to. The grid connection is through modern power electronics to permit rapid switching between either generation or absorption of power. For these systems to become efficient in real-world applications, the system must be able to deliver active as well as reactive power to help with grid stability throughout. And I think this is known.
All right, so a couple of real-world applications that I'm going to discuss are the PHES plants that Moses touched on and stacked concrete towers. So PHES is the most common large-scale use of gravitational energy storage. They account for 95% of all tracked storage globally at over 184 gigawatts. As we mentioned, gravity storage is based on hydraulic lifting of a large mass. PHES does this by with water pumps. During off-peak usage, power is used to pump water uphill into a reservoir, like the one you see on the picture on the right. When the demand for power exceeds what is being generated, water is then released downhill from the reservoir to spin turbines that create electricity. The stack towers are a proposed alternative to gravity batteries that have been envisioned to increase efficiency and match that of lithium-ion batteries. Each tower would consist of a 6-armed, 120-meter tall crane that stores energy using concrete or heavy composite blocks. Excess energy would lift the blocks in the air and then be released when the demand exceeds power generated. This will turn gravitational potential energy into electric energy using a generator. Software has been written for the towers to enhance the dropping patterns for optimized power storage. Each tower is capable of storing around 20 megawatt hours. Go on to the next slide. So the efficiency and cost comparison analysis of these. PHES runs at about 70 to 80% efficiency and are the most cost-effective means of storing large amounts of energy. Though PHES is most widely used, finding a site to build such a plant can prove difficult. In order to produce the most amount of electricity from the gravitational potential energy, the reservoir will need to be placed as high as possible to increase the flow of water. On top of that, there will need to be a large body of water nearby to pump the water from. Many of these plants have to have a man-made lake due to the lack of natural sites, and this will drive up costs of production and could increase the time it would take to compete with the less expensive energy storage methods such as batteries. With stack towers, concrete is denser than water, allowing it to store more energy at the same volume as water. The system will be able to run at 85% efficiency, which is just short of the 90% that lithium-ion batteries can operate at. The cost of delivering electricity after around 10 plants are operating would drop to around $150 per kilowatt hour. This is much lower than the cost to use lithium-ion batteries that run at around $280 to $350 per kilowatt hour. Using the stack tower method to produce power could run for 30 years with minimal maintenance, while lithium-ion batteries last around 20 years and must be replaced. However, a downside to these proposed methods is that the plants will need to be built on site, whereas batteries can be shipped anywhere.
Sorry, I was having trouble unmuting myself there. So on to the conclusion. So as we've kind of talked about, this form of energy actually is pretty widely used today. But the implementation is sort of limited. We saw the limitations of how it needs to be placed. So it has to be in very specific locations for the most part. And there is a short pro and cons list that I've got organized. So we can see that it does give us lower energy costs overall. They last a really, really long time compared to some other systems. And they don't require much maintenance, and I would consider them green. They don't have like huge carbon emissions or anything like that. So it's in general environmentally friendly, other than the fact that it can take up a lot of land. Some of the issues with the system is that it's not quite as efficient as the lithium-ion batteries, but it is relatively close. And of course, there's a large land cost in that they are permanent. So there's no moving them, like Nolan was saying. Once you put them there, that's where they have to stay. So the biggest concern here is the land costs. We have to be able to balance the availability of land and the energy storage demands, because land is just finite. It sometimes creates an environmental uproar because they are so massive. Without land concerns, the decision to use only gravitational energy storage methods to store energy would be obvious. If we were able to store energy as just gravitational energy all the time, it would be the easiest way to do it. And it would make energy costs very, very low. we'll often see them combined with solar and wind energy. So it creates an almost completely environmentally friendly system and renewable energy source. And if we saw them implemented worldwide, again, we would see much lower costs, and it would be energy would be as clean as we've ever seen it. And that is the end of our presentation. Are there any questions?
Okay, so thanks Tyler, Nolan, and Moses for your nice presentation on that gravitational energy storage method. Is there any questions, comments for this group? Anybody?
No questions, but it looked really good and it sounded good.
Thank you.
Okay, thanks. Yeah. Are there any other questions, comments for them? So Tyler, why don't you put like references that you followed for this project, like after conclusion, so you could put few references?
Yeah, I apologize. We have them listed in our paper. We forgot to bring them over, or yeah, I forgot to bring them over whenever I did that.
I would recommend.
I mean, one of the big ones. I mean,
Okay, go ahead. Please go ahead.
I was saying one of the big ones we referenced was gravitricity. We ended up having a lot of slides on that one. But yeah, sorry, you can continue what you were going to say. I'm sorry.
Oh, sorry. So I was telling that after the conclusion slide, you put on more new slide with the like list of references. That will be the title, and then put all the references that you followed. Any internet source, any report, any journal / conference paper, or whatever the sources, please list all of those there.
Yeah, absolutely. Yeah, I'll fix that. Thank you.
Yeah, okay. And then, I mean, you mentioned that VHS is another form of gravitational storage. Did you not notice that, for example, you can lift up some small sized stones or small marbles on top and hold there, and then again, I mean, fall them on a turbine, and then that can produce electricity. I mean, very similar to that VHS, pumped hydro storage. Like in case of pumped hydro storage, during night time, the machine works as a motor, lifts up water. And then during daytime, that water falls on the turbine and produces electricity to meet the consumer's demand. So similar concept, like you can lift up stones with low cost at night and hold there. And during daytime, especially during noon, you can fall those stones or small marbles on the turbines, and that can produce electricity. So I think if you Google a little bit, you will find this one as well that I am mentioning. Okay, anyway, so is there any other questions, comments for this group? If not, then thanks so much for your nice presentations once again. Then by 17th, please upload this presentation file, including that list of references that I mentioned and the report on the Dropbox. Okay, so with that, Nolan, I think now you can leave.
Yeah, thank you.
Yeah, I think you have some emergency, so please you can leave. Okay, then moving forward. So next I'd like to invite like Salman Al-Azmi and Ali's group or artificial intelligence based control approaches for induction motors. So please you share your screen and go ahead.
Hi everybody. Our presentation talking about artificial intelligence based control approach for the indication motor project by Ali Bakreba, Salman Abu Mazen, and Muhammad Al-Ajmi. Next slide, please. For the introduction, induction motor are utilized in light of the fact that work hours industry for an inclusive time as a result of their simple form, high figure and commonly buildable effectiveness. Lately, the research and analysis have gained critical improvement on different kind of control hypothesis and strategy. Artificial intelligent controller AIC may be the most straightforward regular for induction motor control. Next, please. The computational intelligence is a debate for an extended time and can possibly debated forever. However, there is no deny within the uncomfortable fact that computer can have accurate intelligence to assist solving our problems that are difficult to infer by traditional method. Therefore, AI technology are now being exclusive utilized in image processing, diagnostic medicine, further space technology, and knowledge management system, and just to name a few. That is to name a few. While expert system ES and FL rule based and have tendency to identify behavior natural. Next, please.
I will talk. Can you hear me?
Yeah, yes, I can
Yeah.
hear you.
I will talk about the methodology and control algorithm. Intelligent control techniques are generally classified as expert system control, fuzzy logic control, neural network control, and genetic algorithm. Various artificial intelligent controllers are as follows. A fuzzy logic controller. The speed of induction motor is adjusted by the fuzzy controller. The conventional simulated induction motor model, as shown in figure 2, is modified by adding fuzzy controller and is shown in figure 5. Speed output terminal of induction motor is applied as an input to fuzzy controller, and within the initial start of induction motor, the error is maximum. So consistent with fuzzy rules, FC produces a crisp value. Then this value will change the frequency of wave within the speed controller. The wave is then compared with the triangular waveform to get the firing signals of IGBTs within the PWM inverters. The frequency of those firing signals also gradually changes, thus increasing the frequency. As discussed earlier, the crisp value obtained from symbolic logic controller is employed to vary the frequency of gating signals of PWM inverter. Thus, the output AC signals obtained are going to be variable frequency sine waves. The wave is generated with amplitude, phase, and frequency, which are supplied through a GIU. Then the clock signal, which is sampling time of simulation, is split by crisp value, which is obtained from FLC. So by placing 3 sine waves with different phases, one can compare them with triangular waveform and generate necessary gating signals of PWM inverter. So at the primary sampling point, the speed is 0 and error is maximum. Then regardless of the speed rises, the error will decrease, and therefore the crisp value obtained from FLC will increase. So the frequency of wave will decrease, which can cause IGBTs. switched, which can cause IGBTS switch on and off faster. It will increase the AC supply frequency, and therefore the motor will speed up. The inputs to those blocks are the gating signals, which are produced in speed controller block. The firing signals are applied to IGBT gates, which will activate and off the IGBTs. And the second, adaptive neural fuzzy controller. AC motor drives are utilized in multitude of commercial and process applications requiring high performances. In high performance drive system, the motor speed should closely follow a specified reference trajectory. No matter any load disturbances and any model uncertainties. In the designing of a controller, the most criteria is that the controllability of torque in an induction motor with good transient and steady state responses with certain drawbacks. By controller is in position to realize these characteristics. The main drawbacks are the gains cannot be increased beyond certain limit. Non-linearity is introduced, making the system more complex for analysis. Adaptive neurofuzzy combines the training power of neural network with knowledge representation of symbolic logic. Neurofuzzy techniques have emerged from the vision of artificial neural networks and fuzzy inference system, and became popular for solving the important world problems. A neurofuzzy system is predicated on a fuzzy system, which is trained by a learning algorithm derived from neural network theory. There are several methods to integrate an ANN and FIS, and really often the selection depends on the applications. In this paper, the inputs will be EK and delta EK. And the figure 7 shows the overall structure of adaptive neurofuzzy mode.
And I will talk about the result and discussion. A complete simulation model for Scholar V/F controlled induction motor drive, incorporating BI symbolic logic controller, neural network controller, and NFIS adaptive network neurofuzzy interface system. Is developed in an open loop and closed loop system mode. V/F control of induction motor drive with fuzzy controller is meant by proper adjustment of membership function. Neural network controller is meant by adjusting the weight, and ANFIS is developed on a fuzzy system, which is trained by a learning algorithm derived from neural network theory. So as to your simulator result, drive with BI controller speed response has small peak at 0.6 seconds. But just in case of fuzzy controller network, in fuzzy controller network and NFIS, as it means adaptive network neurofuzzy inference system. Controller speed response, it's quick and smooth response, which is shown in the figures 13 and 12. The waveforms of the speed, torque speed, and characteristic. In conclusion, reenactment consequences of the acceptance engine are introduced in customary BI
Hello,
FLC.
Ali, excuse me. Yeah. Okay. Oh, okay, I think now you changed the slide. Yeah, okay, please go ahead. Yeah.
Yeah, I was saying reenactment consequences of the acceptance engine are introduced in customary BI, FLC, NN neural network, and NVIS, as it's evident from the speed prints in 4 models. The fuzzy controller drastically decreases the rise time in the manner which the frequency of sine wave are changing according to the percentage of error from favorite speed, according to the direct relation of induction motor speed and frequency of supply voltage, the speed also will increase. And here we have the references, and that's all.
Oh, so that's all. Okay. So thanks, Salman, Alazmi, and Ali for presenting your project. Is there questions, comments for this group? Does anybody have any types of comments, questions? If no, then thanks again for presenting your project. I think next I'd like to invite JC, Nathan, and Joel's group to present transformers, health conditions, monitoring methods. So please present your project.
Awesome, thank you, Dr. Ali. Let me go ahead and screen share. It's gonna be that one. All right, can you all see it?
Yes, please go ahead.
All right, we're gonna go ahead and start off with Jesse, I believe.
Yeah. Can you hear me?
Yes. I can hear you.
Okay. All right. As you said, Dr. Ali, we're doing transformer health condition monitoring methods with me, Jesse, Joel, and Nathan. All right. Our introduction is transformer monitoring takes in measurements that are acquired through various methods and are used for preventative maintenance purposes to prolong the life of transformers and to determine their overall lifespan before termination. And some of the methods for doing this are our frequency response analysis, the chemical detection, particle discharge analysis, which is close to chemical detection because it's like DGA, the dissolved gas analysis, and fuzzy logic. The measurements are used to see patterns in the transformer behavior, so you can see if there's any irregularities between a healthy transformer and one that's starting to die. But why do we use transformer monitoring at all? In this picture, this is a transformer with a Jacobs ladder where it's extremely high voltage and arcing across. You wouldn't want that in a healthy transformer because the older they are, it is more prone to happening accidentally instead of planned. But why do we use transformer monitoring? The transformer monitoring got started due to how important it is to power the masses for all of the people out there needing electricity. And it would be pretty expensive to repair or replace the transformer itself. But if you were to think about it in a wider scope, it's not only the cost of repairing the transformer itself, because all of the customers who have power are also not being charged for the power. So all of that income is going down as well as the expenses for the transformer itself. So it would be devastating to the amount of income that they have in order to pay for the transformers and the upkeep of all of the integrated network for energy. And now that we have an idea of why it's important to keep transformers up and going, let's go through the methods on how they work. The frequency response analysis for transformers, the transformers themselves have a lot of RLC circuits in them, lots of resistors, capacitors, and inductors. And a good way to test the efficiency of such frequency analysis network is the transfer function. And you can compare the data from the transfer function in the network versus all of the accumulated data that was previously stored in it to check it against a healthy system. So in the first graph, we have the frequency of decibels versus hertz, and it shows a healthy system versus reclamping. And you can see that the peak is higher in a healthy system. The chart A is the high voltage frequency response analysis, and slide B is the low voltage frequency analysis. Next, we'll talk about the chemical detection in transformers. And as I mentioned earlier, the dissolved gas analysis, the DGA, is one of those methods. So it can monitor the heat in a transformer using that method. And if you look at the gases below in this chart, you can see the different types of gases that appear in transformers that once they're detected, you can also go along with the temperature and see how unhealthy the transformer is itself. The first 200 degrees Celsius with the SF6, that is intentionally put in the oil of a transformer because it is an arc resistant oil. It is poisonous, but you don't want arcing to happen inside the transformer. So that's what they start off with to soak in the oil of the insulators and the dielectric of the transformer. And then it slowly degrades over time as chemical reactions take place, and it changes the chemicals inside your transformer as it shows up to 600 degrees Celsius. Then next, coming off of chemical detection would be the partial discharge analysis, because your dissolved gas analysis can actually show partial discharge or PD activity. The only issue with this is it can't pinpoint the location inside of the transformer itself. They end up showing on a graph a sine wave version of it, and then they can try to pinpoint the location inside of the transformer based on this, as shown in that graph below. You got a sine wave going, and then there's noise in the system, and they try to separate the noise from the system to pinpoint the partial discharge, showing the different gases inside of the transformer to let them know that the chemical reactions are happening and that it's starting to get too hot, and it's signs of the transformer going bad eventually. As previously discussed, it is important to keep transformers running at all periods of time because of the money that's involved that you can lose. But the partial discharge acoustic measurement that can be performed on this can be performed on the transformer while it's online. So you don't have to shut the transformer off in order to service it while you're doing this method of testing. And I'll pass it over to Joel.
All right, thanks, Jesse. So I'm going to talk about fuzzy logic, and fuzzy logic uses a combination of the different techniques and assigns a health index to the transformer. And the data factors that go into that are water content, acidity, breakdown voltage, dissipation factor, dissolved combustible gases, and formaldehyde. So water content in the transformer oil has well-known effects on the health of the transformer, which include it accelerates the rate of the aging of the transformer, reduces the dielectric strength, and it can cause bubbling at high temperatures. Acidity of the transformer oil is another indicator of deterioration of the overall insulation system. And so that's going to have an effect on the health of the oil, and deterioration of the paper insulation further increases the acidity. So it's kind of a exponential effect. So breakdown voltage is a measure of the ability to withstand voltage stresses. And that's one of the most reliable measures of the oil quality. Dissipation factor is a measure of the power lost in the transformer oil during normal operation. and it's used to evaluate the electric properties and contamination of the insulating oil. It increases with deterioration of the oil. And so that's kind of how they see how it does is if you have a lot of dissipation, that the oil is deteriorating. And dissipated power is transferred to the oil in the form of heat. So like if there's a lot of dissipated power, then it's going to get really hot, and that's going to further accelerate the rate of aging. So to dissolve combustible gases, all the transformers generate gases at normal operating temperatures, kind of like Jesse was talking about earlier, but they're increased in two cases. And that's when there's a fault in the transformer or when the transformer is just really old. And then there's formaldehyde content. So formaldehyde is the same thing as furfural, which is the same thing as fural or furan. You might see any combination of those things. And it's considered the most important factor in assessing transformer health because it directly assesses the health of the insulation. And so if there's a decline in the insulation health, that's one of the main reasons for end of life for a transformer. So here's the actual test example from the paper I found. And so the left side has all these fuzzy logic rules, and there's certain, some of the data factors, gets sort of rated within those rules. And then all the transformers are on the right side. So if you look at the far right side, third column from the right is rules fired. So that correlates to the table 1. So for example, look at transformer number 11 from 1970. It fired rule number 1. It has a health index of 0.94, which is very bad. VB stands for very bad. So the closer the number is to 1, the worse the health of the transformer is. So the closer to 0, the better. And so you can kind of just see a lot of the older transformers are not in good health.
All right, and this is where I am going to go ahead and take over. So here we have just a list of the components inside of a transformer and what we're looking for as far as breakdowns go. So inside of a transformer, you've got bushings, which are at the very top. And with bushings, you have to worry about partial breakdown between capacitive graded layers and cracks in the resin bound insulation. And of course, moisture is an issue, and then open or compromised measuring tap connections, and then of course partial discharge inside of the insulations. So all of those little faults can cause issues with the actual bushings themselves. And then of course CTs, which are we defined over here, are current transformers. The current ratio or phase error, considering burden, excessive residual magnetism, non-compliance to relative IE or IEC standards. So basically, if the current ratio isn't within spec, it's obvious that there's something wrong with the system. It can check to see if some of the turns are shorted. It can see if there's obviously an open, which if you have an open, you're gonna know about that long before you end up checking any of these systems. Of course, then you have the leads, which can have contact problems, and then mechanical deformation, typically just due to heat. You have the tap changer, which a tap changer is historically been one of the top causes of transformer failures. So the tap changers alter the number of turns in an actual transformer. You can increase or decrease the amount of turns in the transformer depending on what you're trying to do. So that we also have to worry about the insulation, which moisture gets into the insulation, which starts causing it to degrade. And then of course partial discharges through the insulation is a big no-no as well. And then the windings themselves, those are very, very important. If they short between each other, you're going to have major issues. You get a single strand to strand short circuit can occur, which isn't as major as if the full makes full contact, but it's still enough to to cause issues in the circuit, to cause an unbalanced system. And of course, open circuits and parallel strands, short circuits to ground, mechanical deformation typically due to heat. And of course, if the contacts go bad on the actual windings, you're not going to have as good of current flow through it. And then the cores themselves, they can have mechanical deformation, a floating core ground, shorted core laminates, and of course residual magnetism within those that can cause issues with the system. And a few things to notate on the side here: the tap changers, the DTC is 5 positions of operation. It's not usually used regularly. But if it's not used regularly, there's an increased risk of breakdown in its next use, and it cannot be moved while the transformer is energized. And then we have the on-load tap changer, which can vary the transformer ratio while the transformer is actually energized. So that's kind of the difference between those two things. And then we're going to go over just a couple common devices that are, since we kind of went over all the more technical, deeper sides of monitoring transformers, there are a few much simpler ways that we can watch what's going on in a transformer. And one of those is a capacitor voltage transformer. And basically we attach it to the high voltage terminal of the transformer, then also to ground. And what this does is allow us to drop, from 11 kV down to something around, 100 to 150 volts, which can be easily measured with just a normal, a voltmeter or anything of that nature. You don't need sophisticated software to go in and go, okay, the reading looks good. It's continuously been the same reading for the last 2 years, probably not having major issues with the system. And then there's also the current transformer, which is most of us have probably seen. It's just a current clamp. That's what we've been using in lab. And basically it just wraps around a hot wire, and then the EMF field that is generated will be picked up by the transformer, and a current will be induced within the coils, which will cause a current divider based on the number of turns that you have. And with that, you can determine over time whether or not the current's been fluctuating up or down, or if it's just having any issues at all. And then lastly, we have infrared testing, which is probably one of the coolest things that they have, just because of how simple it is. You can use infrared testing to determine the heat of oversized cooling banks. As you can see in the picture, those are cooling tubes for a transformer. So the one on the far right, you can see it's a lot darker than the others. That's a sign that there's not enough oil flowing through it. That could be an issue with the actual level of oil. It could be an obstruction. It could be that it's not sitting level, so it's sitting at an angle. Just all things that you'd want to pay attention to when you're actually monitoring the system. And this can be done, right there in the power plant rather quickly. Some of the other stuff you actually have to send off to labs, like the dissolved gas analysis and stuff like that. So it isn't always an instant result to the test. And if that, we just have our references here. And is there any questions?
Okay, thanks Nathan, JC, and Joel for your nice presentation on that transformer health condition monitoring methods. Is there any questions and comments for this group?
No questions, but no, I thought that was very, very informative, really, really detailed.
Yes. Very informative, right. Yeah.
Thank you.
Thank you very much.
Okay, so no questions, comments from anybody for this group? If not, then thanks again, Nathan, Joel, and JC for your presentation. Okay, so I think for today, our last presentation is electric machines used to lift up objects by Chris, Joshua, and Ryan. So please go ahead.
All right, let me share my screen.
All right. Hello, everybody. My name is Chris Butler, and I'm here today with Josue Fernandez and Ryan Hamling. Our presentation today is on electric machines used to lift things, and we've got several examples to go over with you. We're going to begin today with scissor lifts. There's several different types of lifts, including rough terrain lifts, field-powered lifts, and so on and so forth. But we're going to focus specifically on the electric civil lifts or scissor lifts for this presentation. Go ahead and next slide. There you go. So our first breakdown image shows a typical build for a scissor lift. It's got each component labeled here. Starting at the bottom, you get the base of the unit that's going to house the power source, and that power source is used to extend or compress the cylinder in order to raise or lower the legs. So go ahead to the next slide, please. The starting position will have the cylinder fully compressed with the legs fully collapsed, as shown here. And as it extends, the base of the legs will narrow as the height of the platform rises. Now, the typical, this type of scissor lift is usually catered to, but not necessarily limited to, indoor construction sites, such as a building that's already got its walls constructed, or indoor maintenance, like changing bulbs on buildings with very high ceilings. The compact design of these lifts lend themselves easily to tests such as these. Most of the lifts will comfortably fit underneath the frame of an average doorway when fully collapsed. It allows the user to enter, successfully navigate, and exit the building with ease. And given that they can be simply driven around, they're very frequently much easier to maneuver with than like an awkward extension ladder inside of a building. The efficiency of their design also allows for much greater potential where vertical reach is concerned. Whereas, I mean, if you consider a 60-foot extension ladder, considering the wide base that it needs, it can only reach about 49 feet. These scissor lifts can reach, the platform itself can reach, anywhere from 36 to 50 feet. So if you're considering an average height of a worker, they'll be able to operate at 55 to 56 feet. And of course, once you consider payload, that's another benefit. You're looking, a ladder user is going to have to carry all of their supplies up, but the payload of a scissor lift can range anywhere from 500 to 1,500 pounds. They're very quiet to operate compared to their fuel-consuming counterparts, and you don't have to worry with any leaks or emissions. This allows use inside large buildings during business hours, providing proper maintenance to little or no effect on the company's day-to-day productivity. Now, the motors used in these lifts, they provide more reliability than their fuel-powered alternatives, and significantly less maintenance. The particular motor shown here is a 24-volt, 4-horsepower flex-coupled DC motor. This is a typical motor, as they usually use a 24-volt DC motor, and they range from 1 to 4 horsepower. And they can run off of either a rechargeable DC battery pack or an AC power supply with an onboard rectifier. Now I'll hand it over to Josue next for our next section.
Okay, so I'm gonna be talking about the cranes. That also is an electric machine, and it's used for lifting heavy metal, heavy material, and so the cranes are usually utilized in the construction industry and to lift material, heavy beams, metals, and walls, and depending on the type of crane, it might be, you might have seen it already in some construction area. And the main thing is it just will move vertical or horizontally. And it's divided in two types of cranes. The mobile that are dynamic. I call it. It's called dynamic because they are they can be used for variety of projects like constructing a new building and to replace the heating, the cooling equipment on the roof, and this type of crane is utilized depends upon the high level required, as well as the weight of the object that is going to be lifted. And truck-mounted cranes generally have the smallest reach and they depends on the lifting capacity. The mobile cranes are self-propelled and capable of travel. This means that they power their own movement. And some examples that I can give you is as you see in the slides, the truck mounted, and we have the wheel mounted crane. On the other hand, there are another type of crane called the tower cranes, and you can find them commonly in the high-rise constructions, and are the only type of crane that can be utilized once the building surpasses a height that can be reached by a mobile crane. And in order to support the crane, it must be added and connect the crane to the building. Some of the crane can be on top of the building, and it will be going up and up and up until the sky buildings. And go back to the first. And I want to give you just explain you some examples that we have. The looping boom and also the hammerhead. If you ask what is the difference between those two, it's just for the looping boom tower, it just have additional jeep mobility at the end, and it will lift heavier. It has heavier capacities, and then the hammerhead cranes, but they are more expensive. So that's why you will see hammerhead instead of the looping in some of the buildings, and are especially applicable to working. And the looping boom are you can use. You can see this cranes. Usually, if you go to New York, you will see them every day. And you're gonna go to the main cities in downtown here in US. You can find them everywhere, and they're very utilized. All the information, all the research that I have done, mostly comes from New York, because they try to innovate and improve always these cranes. Next. Now let's talk about the part, and I'm just gonna highlight some of them, and I will go with the boom. That's the main arm of the crane, and apply for both for the tower and the mobile. And the counterweight, you need to have the counterweight, and it's located on the crane, and it just counterbalance the weight of the item being lifted and prevent the crane from overturning. And we have the hook that will be able to lift the material, and it has an aero cap. And for the mobile cranes, there are some variations on the boom. For example, we have that telescoping, which is the boom is comprised of a series of concentric tubular parts, and they can extend or retract. And you can see in the first, in one of the pictures I showed you in the first slide. And then we have the lattice boom that is compromised on metal elements. So, and they are crossed and fastened together, so it spread out the weight and the force. And the shape is like a diamond. For the tower crane, and one of the differences are the mast, which will be supporting the crane, and the structure, which is turntable. It will go at 360 degrees. Let's go to the next one. So motors, and the most generic tower crane, it will have at least 4 electric motors, and they are located in the hoisting mechanisms, slewing mechanisms, trolling, and the jacking up system. So if we go to the lifting motor, allows the vertical movement of the lift. The distribution motor is helping gives the movement of the car along the jib, and we will see the motor of orientation. It's helping that allows the rotation of 360 degrees in the horizontal plane. And then if possible, it will have a translational motor, that is the one that is placed at the base if the crane is mounted. But if this is the case, to move it, the crane has to be at rest. That means no shouldn't be lifting any material. Everything should be reset, and slowly they move it if the tower crane it has some movement in the base tower section. And the work principle on this, just we can spend a lot of time like just going like just in one section, but I just want to highlight some of the main things on this part. So the car operation will drag the whole crane to have the horizontal movement as the direction of the construction field, and it is constituted by a motor and a braking device, and this will like help for the deceleration device and with the wheels. And you have the trolley that will drag the lifting hook to have the vertical movement and the direction crane of the structure. It is constructed by the motor and also have a braking device because it will decelerate the device and wheels. And like the lifting organization, it is used to drag the heavy lifting or descending movements, and will have it has a motor and the deceleration device, a cooling block, and a braking device, and then we have the swing mechanism that we talk about it that will drag the bridge arm to conduct a revolving movement with the shaft at the center, and it will for preventing from the line deflection. It's mainly constituted of a double motor, and the deceleration mechanism have a braking device. So if we go to the slewing unit that is in the middle, and where you see the cabin and the guide section, the hydraulic AC, that's where it is, the slewing unit. And it's the gear and the motor, and will allow the crane. And it has three main parts, and the long horizontal GF, or the working arm that we can call it, which the portion of the crane that carries all the load. And then we have the short horizontal machinery arm, where that we will have all the crane motors and some of the crane motors and the electronics as well. Next slide. So getting more onto one of the sections, this is where the counter jib. I'm highlighting the electrical section with some of the motors, so that's a counter jib. And then you have the hoist unit and the hoist drum, so you can see the electrical cabinet is over there, the angular planetary gear, the electromagnetic shift, and the current brake too. And all of this have the same concept. All the cranes have the same concept, but they will vary on the customer needs. And there are a lot of manufacturing companies. And in the next slide, please. I am showing you the Yongmao specification. This is the STT 2900 model, and just getting into the winch unit. That this is what they lift a lot. You can see that it has, this unit has in number one, the frequency control motor, the brake mechanism, and number three, it will be the gearbox, the hoisting drum in number four, and it will have a limiter and motor ventilator, and at the end is a frequency control system, allows the conversion. The LFV is which will allow the conversion of the three-phase supply from AC transformer to a frequency control supply voltage. Now the question is, one of the questions is which DC motors are preferred for the cranes, the manufacturers, the OEMs, whenever they create, what are the preference? And what I could find is that they like the DC series motors, where the high starting torque is required, because the torque speed characteristic of the DC series motors suit perfectly these frames. And how much they can lift, well, it will depends on the model, but the typical tower crane can have the maximum unsupported height will be the maximum unsupported height is 80 meters, and then you have the maximum reach that will go to 70 meters. And if you want to lift, the powers is 19.8, at least 19.8 tons. And the counterweight always, and it depends on the design also, but in the typical tower that is being used in New York, it will be like 20 tons.
And I'll go next, and I'm going to talk about the articulating boom lift. The boom lift, it's made up of all these different kinds of arms, and it's made to get into some tight spaces. This little section here on top acts kind of like the scissor lift, and it just goes up and down. And then this arm here can swing, it can swing at an angle. And then right here it extends out or booms out. And then you can take the basket here and move it up and down. You can rotate it side to side. They're a lot of fun to drive. This type of machine, it was invented in the 1950s by a guy named Walter Thornton Trump, and he just wanted an easier way to lift things. It started out, a lot of people used it to pick fruit because it was easier than climbing up a ladder with a fruit basket. You could just sit in there and go up and down easily. Then it moved into fire engines. It was easier for them to go up and down and fight the fires than have to climb the ladder. It went telephone line repair, and now it's widely used in construction. It's got a very wide range of motion, and it can reach pretty much anywhere in this section here. I've used them in churches. They're small enough you can drive right through the front doors, and you can get up in there and you don't have to move any of the benches out of the way. You can just park it in the middle and you can change lights or whatever they want you to do. It makes it real easy. It's kind of the same idea as the scissor lift, except just for harder to reach locations. We use them out at the Liberty Bowl, putting up some of those color changer lights. And they're good for tight spaces, and they're efficient and durable, and they're just safer than getting up 50 feet in the air off a ladder or something. They make it a lot safer to work. And there's a bunch of controls in there, a bunch of sensors. Some of them run off gas, but this one here is a battery powered one. It's got batteries and the charger, and it goes to the inverter and gives you a little 120 volt receptacle on board. It's got a level sensor to tell you if it's out of level, and that way you don't overextend that boom arm and risk tipping it over. And it kind of goes along with the tip sensor. It works with a foot switch. You have to push the foot switch down to move the joystick to make it work. So if you take your foot off, it won't run. Now I'll send it back to Chris.
All right, next up we got hoists, stationary electric hoists, to be specific. They're very similar in operation to like a winch that would be used on a vehicle, but these are designed specifically to lift objects vertically. And as you can see on this image here, they'll actually, a lot of them will be able to slide, back and forth on whatever beam they're mounted to. We go to the next slide. All right, this shows your basic components of your average hoist. Going in order of number here. You've got your traveling motor, gear, and brake that's used to move the objects once they're lifted. That's a horizontal function. The next component we've got is the trolley, which is composed of the load beam and the two end carriages. Oh, go back real quick. And then the third unit here is the electrical cubicle, and that's going to house the electrical control system. And then 4, 5, and 6 that we got here is going to be the hoisting machinery itself. That's going to consist of the hoist motor, the gear, the brake, and it's also going to have the rope drum and the hook to fasten to the objects. We'll go ahead and go to the next slide. We got several types of electric hoists. They can range anything from like the smaller one here on the left could be used in your garage at home for personal use. The one on the right here is obviously in some large industrial plant. And the smaller units are going to range anywhere from, weight capacities of 200 pounds or so. And as you can see, the one on the right has a tonnage rating of 3 tons, so they can get up to, they can lift several tons. Most hoists will use a cable or a wire rope coiled around the drum, but some of the more heavy duty ones will actually use a chain to lift some of the more massive payloads. All right, so for our motors, we've got a few different types here that they use. The permanent magnet DC motor is usually applied to low torque battery powered hoists that are most often limited to about 10 horsepower. Due to the permanent magnetic field of these motors, they typically have a higher efficiency than wound field motors, and their direct drive design offers a more compact package with a high starting torque, and they are often much quieter than some of the other options. Now, while the permanent magnet motors are typically more efficient, they usually do, as I mentioned, max out at around 10 horsepower. Now, a wound field DC motor can operate at several hundred horsepower. These units, they're the ones that are most often used in large industrial plants that need to lift, very large loads. Frequently, they're set up as series or shunt wound motors. They're done this way to provide a precise torque speed characteristic that may be required by the particular application. Shunt DC motors are used in constant speed applications, while the series wound motors can be used in varying speed applications. They do consume more power than a permanent magnet motor, but they're very powerful. They've got significantly higher starting torque, and they've got the most torque overall. They're also more efficient at higher speeds. And finally, we've got for hazardous locations, they've got that may have flammable gases or liquids. We've got the explosion-proof DC motors. These motors are typically a sealed design that is intended to contain an explosion should it occur within the motor. The design also prevents the release of explosive gases or vapors into a working environment. And further enhancing the safety of these units, the motor's brush and commutator assemblies are separately sealed in the event that arcing might occur. And this prevents igniting any dust or vapors in the air.
Oh yeah, but he had
These,
a place. Yeah, no, he had a place. He had already planned on going.
Somebody's got their mic unmuted.
Sorry.
These field motors can be either permanent magnet or wound field DC motors. And due to the fact that they're sealed, they're very robust. They're intended to contain an explosion. They're much larger and heavier than a standard motor. The newer units are being produced or moving to brushless designs that'll further the safety of these motors. And now we'll go back to Ryan for the last portion of our report.
All right, the last section will be on elevators. And this one here in the picture is the Bass Pro elevator, the tallest one in North America, freestanding. Basics of an elevator, it's got several different parts. There's the car, that's the part you ride in. And then there's a counterweight and that's probably the most important part of the elevator, but we'll get to that here in a minute. And the electric motor that pulls the load up and down, and on a series of cables and pulleys. And then there's some safety systems in place as well, just in case one of those cables snaps or something else goes wrong. Now, the counterweight is very important in the power consumption because the elevator car plus the occupants can get heavy. And if that motor had to pull that whole load up and down the elevator shaft all day, it would take a lot of power and there'd be a lot of heat built up. And it would cause a good strain on that motor. And so the counterweight cancels out a lot of that strain because it's weighted close to the weight of the fully loaded car. And so the motor only ever has to lift the difference between the two weights instead of the entire weight of the car. So it puts less strain on the motor and uses less energy. And the elevator is full of control systems too. The entire hoistway is just filled with wires and cable trays. Some of the inputs are, the car call button and the sensor inside the elevator that senses what level it's, or if it's level and what floor it's on. And then it'll output the sound and the number of the floor and the arrival sign, and it'll open and close the door whenever it's done. And that is all we have. Do you have any questions?
Okay, so thanks Ryan, Chris, and Joshua for your nice presentation on this topic. Is there any questions, comments for this group from anybody? No questions, comments from anybody?
No questions. Sorry about the unmuting there, guys. My bad.
No, it's fine.
Oh, you're good, man.
Go ahead. Nathan, do you have any questions, comments?
Oh, no. I was saying it was a good presentation. I just wanted to again say sorry for interrupting their presentation.
Yeah,
I feel bad.
No, that's fine. Yeah. So Alexandria Golden through chat, but she said very nice presentation. Okay, so with that, I think that's all for today. So I think every group presented well. So let's give them big hand for every group. So thanks everybody. And please upload your presentation slides by November 17th on the Dropbox, as I mentioned in the email, together with the report. With